Batteries are one of the most important technologies used by any electric vehicle, and Tesla already has some of the best. Tesla is soon going to update us on its latest battery technologies, and this video will provide the information that you need to understand those updates. Tesla published a detailed patent in October 2017 that gives us a lot of information about its battery pack design, and another published in October 2019 that gives a lot more information about battery pack design for static storage. It also published a patent in December 2019 with details of additives to the battery electrolytes. We will look at these in more detail in a moment. But note that a company such as Tesla will try and patent any good ideas its teams think up, even if it doesn't plan to use them. But it will make doubly sure it patents any ideas it does plan to use. The timing of the Battery Day announcements is highly likely to be dependent on the completion and publication of a whole string of new battery-related patent applications presently going through the patent process. When the patents are granted and published, we will have our Battery Day, or not if the patents are not granted or get delayed. Tesla uses cylindrical battery cells in two sizes. It started with the 18650 cells and then moved to using the larger 2170 cells. Tesla doesn't provide a lot of details of the performance of its individual battery cells, but luckily for us, NASA has recently been evaluating off-the-shelf battery cells for its next Jovian mission. If Tesla gives us its figures for its new batteries on Battery Day, then we will see how they compare with these figures from NASA's studies. NASA tested 18650 type cells from the leading manufacturers. The Samsung batteries can store the most energy per kilogram, but the Sunny batteries store the most energy per litre. We can expect to see the new Tesla batteries beating both these figures. When tested for cycle life at 0 degrees C, the LG Chem cells are distinctly the best. LG Chem cells also come top for cycle life at 20 degrees C. NASA scientists pulled cells to bits to see what was inside. There are quite large differences in the internal structure of cells between manufacturers. All the cells tested have graphite-based anodes. That is something that may change for the new Tesla cells, although the December patent is for additives in graphite-based cells. There is some slight variations in the chemistry of the cathodes in these tested cells and in the makeup of the electrolyte. But unfortunately we don't have detailed figures for the percentage of elements like cobalt. We know that Tesla has been reducing the percentage of cobalt in its cells and aims to reduce it further. Note that Samsung cells also uses a small amount of silicon. This may be as silicon oxide that Tesla uses to absorb expansion and contraction within the anode. All cells show growth of impedance over many cycles of charge and discharge. LG and Samsung have the least, that is desirable. NASA's conclusions are of particular interest. The LG MJ1 and M36 cells have been picked out as having the most useful balance of properties for their Jovian mission. What is also particularly useful for electric vehicles is that these have most of their energy available at normal driving temperatures. When Tesla presents information about its new batteries on Battery Day, we can compare Tesla's figures with these LG batteries as best in class for the commercial competition. Another comparison that we need to make is with the NCM 811 pouch cells from SK Innovation, from Cattle and from LG Chem. This is a low cobalt cathode-based nickel cobalt manganese cell. We know that Tesla is also taking an interest in these pouch cells. SK Innovation is using anodic material that has nickel, cobalt and manganese in the ratio of 90%, 5%, 5%. It is also increasing the silicon content of cathodes and using novel materials to control expansion and contraction during charge and discharge. It has made claims that it is approaching 700 watt-hours per litre, but not yet in production. Envision AESC, which supplies NCM 811 cells to Nissan, is claiming 300 watt-hours per kilogram. Samsung SDI is also claiming a new battery going into production at 500 watt-hours per litre. There are two main problems with current battery cell designs that prevent higher energy density and longer cycle life, but these are problems that are being solved. One of the biggest problems in our otherwise most potentially desirable batteries is that the volume of the anode or cathode changes as the battery charges up and then discharges. These volume changes soon start to break up the structure of the battery, breaking up the anode or cathode, breaking up the important layers that form between the anode and cathode that allow a rechargeable battery to function. Tesla already uses a matrix with some silicon oxide that allows a small amount of expansion and contraction to increase the life of the battery. Some researchers have demonstrated how it is possible to look inside a battery and see how its structure changes as it ages. Researchers have discovered that it is possible to carefully control where this expansion and contraction takes place, and by creating tiny spaces within which nanograins of the electrode material can expand and contract, the bulk material no longer breaks up. Some researchers have created a sponge-like matrix. This example is in lithium-sulfur batteries. Others have created a matrix of tiny tubes of graphene, or a nanoscale array of tubes of mixed ionic electronic conductors. The expansion and contraction of the lithium metal nanoparticles then takes place within these tubes without impacting the bulk structure of the electrode. An electrode using nanoparticles of silicon in a matrix that controls expansion is also distinctly possible. New designs for this matrix would allow the same mass of battery to hold a higher charge, to charge faster, and to last much longer without changing the battery chemistry. Production of these batteries also requires new methods of producing uniform nanoscale particles of the electrode material to fit inside the sponge or tube matrix. Creating nanoscale spaces in tubes or sponges for expansion and contraction within the battery is the key to solid-state lithium batteries, where the expansion and contraction of existing prototypes cause them to break down within a few hundred cycles. I expect that we will hear that Tesla's team working on these solid batteries is now achieving thousands of cycles. These expansion-tolerant battery designs will also allow rapid charging to a higher state of charge and discharge to much lower values without impacting the life of the batteries. Another common problem to our battery cells is the nature of the layer that forms between the electrode and the electrolyte. This layer needs to be stable and keep its structure through many thousands of charge and discharge cycles. In early designs of lithium metal batteries, this layer was unstable and tended to grow needle-like crystals of lithium that could cause the battery cell to fail. Some researchers have developed techniques to explore the structure of this interface and to design polymer composites that create a much more stable interface. Others are developing solid ceramic electrolytes to perform the same function, for example using a nanolayer of boron nitride. Both these polymer and ceramic composites can be designed to be non-flammable. Some even include a fire-retardant additive such as decabromo-diphenyl ethane and can be solid-state rather than liquid, avoiding the risk of batteries contributing to a fire in an accident. Tesla's battery patent from December 2019 describes the addition of several chemicals to stabilize this interphase layer. Some researchers have been looking at the manufacturing methods for these new battery cell designs and have developed low-cost methods of creating these new electrode and electrolyte designs, such as mixing the electrode nanoparticles together with the nanotubes in a water-based slurry before forming the electrode layers and drying in vacuum. I expect to hear from Tesla that use of new interface polymers is resulting in higher energy densities and stability over many more cycles of charge and discharge. For the future, these techniques for using nanoparticles in the electrodes for controlling expansion and getting a much better understanding of the electrode-electrolyte interface are likely to speed up the development of other battery chemistries. Others to watch are lithium-sulfur, sulfur-bromine, and potassium-ion batteries. More accurate and rapid temperature control of the battery pack is also likely to feature at Tesla Battery Day. Some Tesla patents for this have already been published. Tesla has detailed records of the long-term performance of its batteries and knows how few need replacing. One development we are likely to see is a dramatic simplification of the battery pack and its supporting structures. This could be the creation of the floor of the car as a single new casting that forms the cooling and heating plate and includes the cooling channels and all the supporting structures for the individual cells, plus new wiring harnesses that simplifies connection and control of individual cells, doing away with the need for a separate battery pack casing and the battery modules and reducing the manufacturing costs. In Tesla's recent energy storage patent, each battery cell is insulated from the next. Heat from each cell is transferred from the cell to the cooling plate it sits on by heat pipes, hollow fins partly filled with a liquid. This liquid evaporates using heat from the cell and condenses against the cooling plate below. Liquid flowing through the channels in the cooling plate removes the heat, and capillary action within the hollow fin returns the liquid to the hot surface. The direction of heat flow can be reversed by heating the fluid pumped through the basal plate, and the hollow fins will now efficiently transfer heat back to the cells. Tesla plans to use a heat pump to heat or cool the circulating fluid, and also to be able to store heat in a heat reservoir to increase the efficiency of the system. These developments could also be applied to an electric vehicle battery pack. More attention to rapid heating and cooling of these cells results in optimal battery temperatures for charging and for supplying the motors, and for cooling to the optimal temperatures when not active. Such a battery management system would use more energy, but result in much greater efficiencies overall and longer battery life and optimal fast charge rates. I could also anticipate a new battery cell that is built with a heat pipe at its core. Plus, this new cell could have an outer layer of insulation that contains a fire retardant chemical. Each cell would sit on a spike cast into the battery baseplate, ensuring it is precisely located in place, and the baseplate has the cooling and heating channels ready cast into it. Note that the Tesla Semi needs these battery advances. So in summary, we are likely to see all the desirable qualities of Tesla batteries enhanced, some quite dramatically. We are likely to see batteries that are cheaper to manufacture, charge faster, and last longer. We are also likely to see numbers of new Tesla battery patents published at the same time. We are also likely to hear about the development of Tesla's own battery production line for its own new batteries. A list of references is included in the video description. These in turn link to the research publications that form the basis for this video. I hope that has been useful. Thank you for watching. Please subscribe to this channel.